So we have seen different graph sampling methods at the node level, the layer level, and the subgraph levels. And this is basically to form the mini batches for our stochastic gradient descent, loss optimization, and weight updates. Now, one issue that comes with batch-based training is what we call the covariate shift. So the covariate shift here, if you look at these, learned representations or embeddings, okay? So the first dimension and the second dimension, so F1 represents the first dimension of our learned vector, okay? The learned representation. And we have also the second dimension here, F2. And this is for layer 1, for the first layer. If we take a single layer, so layer 1, all right? And if we look at the relationship between these two covariates or these two features in our learned embedding in a particular neural network. So this is taken, by the way, from the textbook Machine Learning Refined by Jeremy Watt, chapter 13, section 6. So this figure is really beautiful because it shows us how the change or the variation in the covariate shift as we train the model. So at the beginning of the training, you can see the loss function here. All right, so this is our loss function. And these are the parameters that we want to optimize. And as we iterate, as K basically increases, at the beginning, we have this kind of distribution of, the relationship between these two features, F11 and F21. But then as we start optimizing, as we start, kind of our gradient descent, we see that the shape changes, okay, of this relationship. And then towards the end of the training, it dramatically changes, it shifts. So there is what we call a big shift between even two consecutive iterations. You can see that moving from this point of, the optimization iteration to the next one, there is a big change in the relationship between the features, which means our model is not stable. Because remember, guys, these features are the output of the activation function, and the activation function takes in our W, or our transformation, right? And if we're doing aggregation, we're going to add the aggregation in a GNN model. So all of this goes into the activation, and after you get your activations, you get the features or the learned embeddings right here, the new representation. So this new representation is not stable, okay? Is unstable. So unstable is this instability presents a big problem. So that motivated the proposal or the introduction of the batch normalization, okay? So the batch normalization, or the BN layer in a neural network, it aims to to stabilize the GNN training or deep learning training in general. So batch normalization, or batch norm, it shifts and rescales each activation H, right? So that the mean and variance across the batch become values which we are learned during the training. So let me explain. So basically, if we have the distribution of the HK of our node embedding, particular node embedding, we're going to have maybe a distribution like this. And then for HK plus 1, we will have a very different distribution, right? So this kind of shift, dramatic shift or jump or big variation in distribution does not allow the network to stabilize in training, because basically the distribution of each batch changes, impacts these learned embeddings. So because, as I mentioned earlier, if we have, batch 1, B1 with a particular distribution, and B2, then you go over B2 with a second kind of distribution. So all these, shifts in distributions, they will not help, like the network to kind of converge and, stabilize in its learning. So the idea is to kind of constrain or to bring all of these batch distributions into a single uniform or predefined distributions with a mean, a shift and a scale to learn, okay? So with a particular shifting and scaling parameters to learn, let's call them, here we have gamma and we have sigma, okay? delta, sorry, delta. So let's look at this. So first we calculate the empirical mean of all elements in the batch. So we take the embeddings of all nodes in our batch in a particular GNN layer. So this is done for each layer independently. And so this depends on particular layer, of course. So we can add the layer here if we want. So we can put layer K, right? And this is layer K. Right, so we can add the K's here everywhere if we want, but this is a generic, I would say, formula. All right, so now we calculate the if we add it there, so we can put here also K, etc. So we can add it everywhere if we want, but let's keep things simple for now and articulate that. So basically, we take the mean of all nodes in a batch. So if we have, you know, a graph like this, right? And these are the sampled nodes. So we're going to take the mean embedding of all these nodes in this batch B. Okay. Now, and also we do that, we take the standard deviation. So we compute the mean and variance over the batch B elements, you know, over B embeddings in batch B. And next we do the normalization. So the batch normalization, basically we normalize each node embedding. So the node embedding of node I at layer K, right? So we're going to use the computed mean and variance. So we will take the mean out and divide here. So this operation right here is just, you know, the normalization process that we have. And then this normalization process, it brings everybody to a zero mean. And we add an epsilon here to avoid dividing by zero, division by zero, okay? So now for each node in the batch, for each node I in the batch, we will basically update its embedding by doing this operation. And this operation, it takes in two parameters, a scaling parameter, gamma. So this is learnable per layer, scaling parameter. And then we have a shifting parameter. So both of these are actually learnable, so we can optimize them. So we can add them if we have, you know, we have our W, we have our beta, the biases and all of that. So we're gonna add these, you know, two scalars, the gamma and the delta, in our parameters to co-optimize for our network for this particular layer, GNN layer that includes a batch normalization, okay? So now the benefits of the batch normalization, it has a lot of benefits. So the first one is the higher learning rate, which the batch normalization, it kind of smoothes the surface of the loss. So the gradient changes in a more kind of, you know, flowy way. So this reduces the problem of zigzagging, where we have zigzagging, remember guys, happens when we have seen that when you do training stochastic gradient descent for each point individually, you will have different kind of shattered gradients, and that, you know, makes the zigzagging like this to the optimum, right, if you have your loss function. Now, the batch is the same if you have, you know, this batch, the first batch without any normalization, and you have the second batch. So these will have also different kind of, you know, average directions, and that will cause some, you know, shattered gradients, which means, you know, your gradients will get shattered in terms of directionality. So to kind of, you know, bring them all to the same direction, you do the batch normalization. So one can, in this case, if you smooth the function, if your loss function doesn't look like, you know, kind of very, so this is not something, maybe, I don't know, it seems like something like this. So your loss function, if it looks smoother, if it's smooth, then you can increase the learning rate. You can jump, you know, make big jumps, right? But if it is not, if it's kind of, you know, very, it has a lot of narrow areas, right? Then you cannot use a high learning rate. So you need to kind of decrease your learning rate. And in this case, basically to avoid, you know, like, for example, if I do a big learning rate here, I may miss some local optimum, but maybe I wouldn't have something better later on. So we can't see that because it changes dramatically and quickly, right? So yeah, so using higher learning rates with batch normalization. Also here, we can see that it regularizes. So as I mentioned, there is randomness here. And when we take the batches, so when we do the here the BN, the batch, when we add the batch normalization layer, this injects a sort of noise to the training process because the normalization depends on the statistics of the entire batch. So remember, the distribution of the batch impacts the learning. So here, the distribution of the batch impacts our learning. So somehow, as we do the gamma, the shifting, and the scaling, and this becomes learnable, somehow this could be considered as a perturbation that we are introducing to our data distribution. And this perturbation allows us to kind of, regularize the learning. So there's a lot of research on this topic, very high level research and really exciting research. But yeah, so just in a nutshell, telling you guys about these kind of important kind of properties of batch normalization. I may add some references as extra resources for you if you want to read more on this. So injecting noise makes models generalize better, and this is something that has been observed over and over again in the literature of deep learning. So for example, here, the activation of a given training sample, a given node, right? It will be, so let me just, a given node. So the activation here, remember, when we do the activation, we get the H, the final embedding. It's based on the activation of all this formula, that the message propagation formula that we had, right? So this will be normalized by an amount that depends on the members of the batch, because remember here, the formula we have, the HI has been normalized with respect to first the mean, MH, and the standard deviation. And this mean and standard deviation depends on the batch, on the batch itself, the elements in the batch, because it's calculated over the whole batch. And then we learn the scaling and the shifting. So in this example, basically, the normalization somehow, it depends on who is with you, right? So you will have a completely different mean if you have different members. So this mean, of these nodes, let's call it mean 1, will be different from mean 2 if we have, for example, these kind of nodes, okay? These 4 nodes, for example, in a batch. So these will change, and because of that, they will be processed slightly differently depending on the elements of the batch. And this is basically considered as kind of, it introduces variation into the learning and a sort of randomness also that is controlled by the scaling and the shifting, and also by the normalization. So we always want to have a controlled sort of kind of a randomness to not let things go out of the way. So the last thing here is stable forward propagation. So in this case here, we have, let me remove this. So BN, it allows to control the variance of the learned embeddings. And this is, through the scaling and the shifting. So we are controlling the HI. So here it receives, gamma HI plus delta, right? So at each layer, going from layer K to K plus 1, we are controlling, the distribution of the embeddings. So this allows for a stable forward propagation through the scaling and shifting that is learned at each layer. So of course, the mean and the standard deviation, they depend on the batch, but these scaling, we will learn them at each layer, so we can bring everybody almost to the same kind of distribution, but not identical, because we want some diversity in the learned embeddings from layer to layer. We don't want HK, we don't want HK to be equal to HK plus 1. It means like we want them to be different, but we don't want them to be divergent. So divergent is really something like, extreme, okay? So here, between the 2 consecutive layers, so we want to control the variance of the learned embeddings between consecutive layers K and K plus 1. And this stabilizes the network transformation functions, which are our mapping functions W, right? So the W function and any other parameters in the transformation that we're learning are the features between neighboring layers. So the network can easily control its own learning path and in a more effective way. So there is some control over there. And here we can see this clearly in this figure. So when we add batch normalization, you guys can see that even if the distribution of the covariates is changing, it's still, oops, let me use this one better. It still follows the same path. So here, let me bring, all right. So it still kind of follows the same direction. So it is kind of, you know, being scaled a little bit, right? Like there's a scaling there. You can see the width here, right? But still, you know, it has the same direction. So we're learning the same relationship between these covariates that will control, you know, like the final output, right? So you can see as we learn or as we keep on optimizing our loss function, we are, it's still stable. And you guys can also notice clearly that the loss function is much more stable, it's smoother compared to the first one on the same data set. So adding this kind of, you know, batch normalization, it smoothed the shape of the loss function. And this is what we have seen before. So that's why we can use higher learning rate. It is regularized compared to this one that is a bit kind of, you know, it's not very smooth. All right. Cool. So that was